we're going to take a look at molecules and polarity and see if we can sort out what some of these things are for you. Okay. Why are we doing this? The physical properties of a substance are dictated in part by whether or not a molecule is polar. For example, oil and water do not mix because water is polar and oil is nonpolar. Another example is carbon dioxide and water. At room temperature, carbon dioxide is a gas while water is a liquid because carbon dioxide is nonpolar while water is polar. In this activity, we'll explore the factors that contribute to a molecule's polarity or nonpolarity. And one thing to remember, it's the polarity that allows the molecules to either stick together or not stick together to a greater or lesser extent, depending on the strength of those polarities. And that's what leads to some of these here. So we're going to look at how do we determine if a molecule is polar or nonpolar. So we are going to start off with examples of nonpolar and polar molecules. Okay, so a wide variety of them here. Here's a bunch here. Here's some more over here. And here are the polar molecules over here. These are all polar molecules, and here's how we tell the difference between these things. Right? We have to know how the polar bonds or nonpolar bonds are arranged here so that we can determine what they are. So we have polar bonds in a bunch of things. Here's a polar bond, 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 here's a nonpolar bond, here's the nonpolar, nonpolar, nonpolar. So hopefully you can see that nonpolar has a darkly shaded and lightly shaded circle, and the polar bond is a darkly shaded circle and an open circle that is not shaded. And that's how we tell the difference between the polar and nonpolar bonds here in this model. So let's take a look here. Let's see, we just talked about this. How is polar bond differentiated from a nonpolar bond? By color. And that was easy. All right, number 2, formaldehyde has the chemical formula CH2O and it is trigonal planar. Draw this molecule using open and shaded circles as it might be shown in model 1. So let's take a look at what our Lewis structure might be. Here is our carbon and oxygen and the hydrogens on it to make formaldehyde. It's trigonal planar, so all these angles are 120 degrees. That one, and this one, these are all congruent angles on there. Okay, and so it's trigonal planar. So how would that look? Well, we've got our central atom here that is darkly shaded. We have a polar bond. Now, how do we tell that the carbon-oxygen bond that I see here is this polar bond that we have here? Use electronegativity difference to tell if it's polar or nonpolar. Okay, so that's what I do. I look up the carbon and oxygen, that's polar, carbon and hydrogen. Oops, I want circles on here. This one is a shaded circle, and this other hydrogen is also a shaded circle, though that's too small, but that's how I'm going to do it. I'll fix it. Here we go. Just for you guys, because I love you so much. Here we go. All right. Again, not great, but that's fine. Do it all good right there. There we go. Shaded. That's better. Okay. So that's how it might look if we look at model 1. All right. So 3. Label each diagram in model 1 with the 3-dimensional electronic shape that it represents. Okay. So this is a big thing for you to do. If we go up here and take a look at these, and let's squish them down a little bit so they fit on the page. All right, here they are. Here's what you need to do. Use your Vesper PDF to determine shapes. And how do you do that? Well, you go and you take a look at some examples here. For instance, this has 1, 2, 3, 4, 5, 6 things bonded to it. And if I go and look on Vesper for 6 bonds, 0 lone pairs in that, then I find that this is what we call octahedral. Right, I'm going to do a couple of these that are difficult for you just because you haven't seen them. Leave the simpler ones for you. So that's octahedral, makes this one over here with 1, 2, 3, 4, 5, 6 things on that, also octahedral. Right, here's one that has 1, 2, 3, 4 bonded atoms and 2 lone pairs. So I would look for that. There's 1, there's 2. And when I find that on the Vesper sheet, that tells me that this is square planar. And you can do the rest the same way. You work your way through, looking at that Vesper sheet, finding all the things that are attached, lone pairs and bonds, count them up, find them on the list, draw your structure's name off that page. All right, so I'll leave you to finish up the rest of those while we go back and take a look at these. All right. Let's see, can the shape of the molecule explain polarity? I'm going to say no, because there are many shapes the same on both lists. All right, so if the shape's not different, see the same shape on both sides, then that can't explain why some are polar and some are non-polar. All right, so now in this one, we're going to say, take a look at, do polar molecules or non-polar molecules contain polar bonds? So go back up here. We are looking for these polar bonds. Do they exist? Well, here's a polar bond. Here's a polar bond. Here are 2 polar bonds on here. This one has 2 polar bonds. This one has 2 polar bonds. This one has 4 polar bonds. All right, so here's all these polar bonds. It looks like both nonpolar and polar molecules have polar bonds, but notice that not all of them, right, contain polar bonds. Many of them do, but some of them don't. Right, so let's go up to our answer sheet here. And so it looks like nonpolar molecules may contain polar bonds, and polar molecules may contain polar bonds, but there's no guarantee. It doesn't have to be either way. So let's see what the student says. He says polar molecules are just molecules that contain polar bonds. If there are no polar bonds, then the molecule is nonpolar. Do I agree? I disagree. There are nonpolar bonds on both lists and some molecules on both lists only have nonpolar bonds. Okay. How is a lone pair of electrons depicted? We saw that. Those are dots, right? And let's see. Nonpolar molecules may contain lone pairs, and polar molecules may contain lone pairs. Let's take a look. Go up here back to the top so we can take a look at them. And look, here's nonpolar molecules have lone pairs of electrons, and polar molecules have lone pairs of electrons, but not all of them. So let's see this. So it looks like our nonpolar molecules may contain lone pairs of electrons, and polar molecules may contain lone pairs of electrons. They don't have to, right? Is the presence or absence of a lone pair of electrons sufficient to explain polarity? No. some don't have them. On both lists. All right. Okay. When polar bonds are present in a nonpolar molecule, how are they arranged around the center atom? On the same side or opposite sides? Same with nonpolar bonds. How are they arranged around the center atom? Same side or opposite sides. We want to look at nonpolar and polar molecules and see how the polar bonds are arranged. Okay. So if I look here at some of these, well, this looks like I've got two polar bonds on one side of the molecule. Here's a polar bond. These appear to be on one side of the molecule. On one side of the molecule for polar molecules. For nonpolar molecules, it looks like they're on opposite sides or both sides, or in this, they're all over, right? Here's one and there's two on the other. Here's one, two on the other. Here's one, two on the other. So it looks like they are either on opposite sides for nonpolar and same side for polar. So let's answer that one down here. Looks like nonpolar molecules, they are on opposite sides, right? Polar bonds are. Polar bonds. In a polar molecule, right, they are on the same side of the molecule. All right. When lone pairs of electrons are present in a non-polar molecule, right, and when lone pairs of electrons in a polar molecule, how are they arranged? Are they on the same side or opposite? So go back and look. Let's see, this is on one side. These are on one side. This is on one side. These are on both sides or all sides for those. So let's go back to our questions. When a lone pair of electrons are present in a nonpolar molecule, they are on nonpolar molecule on opposite sides of the molecule. When lone pairs of electrons in a polar molecule, they are on the same side of the molecule. So lone pairs, nonpolar, polar. Lone pairs on nonpolar are opposite, and lone pairs on polar molecules are on the same side. So consider the term symmetry. As a group, rank the following shapes. All right, so we know that circles, no matter how you divide it in half, you get symmetry in an infinite number of ways. So we're going to make that one number 1 for the most symmetric. Okay. Then this rectangle here, I can put it, divide it this way, and I've got 2 equal halves. I could divide it this way, and I get 2 equal halves, and that's all I can do. And so that's going to be next on the list, I think. There, this. All right, I think here's where we are. We had a little glitch with our program here. So this was 1, this was 2. All right, this triangle, if I divide it in half this way, I get 1, so I go from infinite to 2 to 1, so this will be number 3. And least symmetric, there's no way I can do this. This has no symmetry. You can't divide it in any way and get it to fold over on itself and look the same. So this will be 4 for least symmetric over there. All right, which set in model 1? The nonpolar molecules or polar molecules contain molecules that are symmetric about multiple planes of symmetry. Okay, so let's go back to multiple planes. Let's see, this one, I could find symmetry that way, or this way, or this way. I can find symmetry this way and this way. Here, I think I can find symmetry one way there. I can find it one way there. Right? This one, if I could, was rotated, I could divide it in the middle there, I think would be the only way. So around one axis, this one around 1, 2, 3, 4 different axes. So it looks like my nonpolar ones. Look that way. So nonpolar molecules have symmetry around multiple planes. Okay, that's important. That's how we tell the difference between the polar molecules and the non-polar ones. Okay, so read this. Polar molecules have an unequal distribution of charge around the molecules as a whole. This could be due to a bond being polar or a lone pair of electrons being present. Both would cause a concentration of negative charge on one side or in one area of the molecule due to an unequal distribution of electrons among nuclei. Okay, so polar molecules, uneven distributions. If a molecule has more than one polar bond or a lone pair of electrons and they are symmetrically arranged, there is no unequal distribution of charge and the molecule is nonpolar. Okay, so suppose a molecule contains two bonds around the center atom and both those bonds are polar. What would the angle be between those two bonds for the molecule to be considered nonpolar? Okay, so I need a center atom, and we'll put on one polar bond. Now, where does the other polar bond have to be in order for this to have symmetry? Well, the only place it can be is on the other side, right? And so this angle here would be 180 degrees, right? 15, suppose a molecule contained 4 identical bonds around the center atom and all 4 of those bonds were polar. What would the angle of the 4 bonds need to be for the molecule to be nonpolar? All right, well, that's a tetrahedron. We're going to have our central atom here. If I have a polar bond here and a polar bond here and a polar bond here and a polar bond there, and they are all symmetrically arranged, every single one of these angles is 109.5 degrees. Okay. If I have one polar bond and no lone pairs, can it be nonpolar? No. Like it says right up here, right? If a molecule has more than one, right? More than one, right? You need more than one for symmetry. Right? All right, here's where I want to stop. Finish the rest on your own. Right? You have all the tools now. You should understand what's going on. So good luck with where this is, and send me any questions that you have as you work on those. If you can do it during the day or whenever you happen to be working on it to get this done. Send me notes if you have questions, and I will see you guys back in class.